So, do you
Yes,
have
sir.
any doubt whatever we did yesterday? Anything from that you want to ask before we will start further? So, if you have any doubt from previous one, you can ask.
Hello, sir.
Or if you have any doubt from whatever we have covered so far, so you can ask that one. Otherwise, we can start for the new part.
Sir,
Yeah.
sir, zero shear stress is not clear.
Uh, Zero shear stress means, let's say you have just like a solid material, or let's say you have this much of, or maybe for time being, you can consider this particular the notebook. Fine. So in that, let's say you are applying some force from this side, some from maybe on this side again, maybe from top side, maybe from bottom side, or you are free to have this have currently six sides, so you can apply any amount of force on that. Fine. So zero shear stress condition says that if you are applying a normal force, it will give the normal means the stress, or that's called actually pressure or compression part. If you are parallel to that, it will give you the shear stress, or we can say the tangential component of the stress that is treated as shear. So you can say all uh, total of all these means the stresses must come equal to zero. That is the meaning of zero shear stress. It doesn't mean that we are not applying the force on that, but you are the applying force in such a way that total the resultant all the stresses is coming zero. That is the condition of zero shear stress. Is it clear now?
Yes, sir.
So the zero means either you means the apply the forces in such a way that the total of all stresses should come zero, or you don't apply any force. You have two conditions, right? Is that fine?
Yes, sir. Thank you.
Any other? So we can start now, right? Can we?
Yes, sir.
Okay.
Yes, sir.
So very good morning to all of you. So today we will start from where we have left yesterday. So yesterday we have talked about some definition of fluid mechanics and its various branches of the fluid mechanics applications part. So we were ended at this particular point that this fluid mechanics have ample number of applications in daily applications as well as industrial applications. Just like in this figure, we were here that you have wind turbines. So you have to in wind turbine you are extracting the power naturally from uh, the natural blowing wind only. So you have to design these blades in such a way that this should run as much fast as possible, even if the normal wind conditions. At the same time, in case of a storm, something they should survive also. It's not like that they are very light material, something. So designing must take care everything in that is stability part and at the part of its moving part, the dynamic part also. In case of the industrial piping here, you say the in all industrial plant or maybe wherever you want a distribution system. So distribution, the system one you have in your hostels where you are the distributing water in each and every hostels and bathrooms. So that is also the distributing the system that is called a network actually. So any the network maybe of gases, maybe of petrol, maybe of your water. So if you have a fixed locality and fixed orientation where you have to distribute the something on a regular basis, so in that case you can lay down the piping. So you have these pipes. So what the pipe have? You have a measure a the, means the straight pipe Then you need the several connections to that. First, somewhere you need a larger diameter pipe, somewhere the smaller diameter pipe, just to control your flow rate and its velocity and pressure. Second part is that then you need something to change the direction. So to change the direction, either you have to add a band or elbow. So you can see in that these are some direction change parts. So these are called some bands or elbows. Then you need to connect the pipes here. So to connect the pipe, you need a socket, you need the nipple. So where you have the threads on both the ends, right? You may have threads also, and these days you have push and pull type of the connection. You don't have thread, just like in your butter purifier, where you connect the tubes of your butter. You don't have their threads. You have just push and pull type connections also. So those are also quite functional these days. Then something you need to control the flow. So to control the flow, you can see in this figure, this is your control valve here. So this will control your flow, depending on need. So valves are must two purpose. First, to control. Second, in case of something went wrong after a particular point, and if you don't have valve before that, your entire material will go as a base. So the disasters things cannot be controlled. So every subsequent kilometers or half a kilometers, just like your petrol pipelines, you always put a pumping or a substation there. There you have valves. So this you can say on a larger scale, the third figure industrial applications here, you have so many things here. You can see valves here, and all these you have the insulated pipes here. Now you can see these figures. These are the the insulation connections. In this pipeline, you can see there are no insulation here. So we were here in the yesterday. Now beyond that, now we have something it's called no slip conditions. So when we have the means, let's say this is the contact here. Now as far as you are something far away from it, you are free to move anywhere. As you will go closer to the surface, you will become very conscious, and as you will become very close, again further conscious. Now at the condition will come the time you will touch it. So the time you will touch, you cannot move, you are not free. This surface would also move with you. So the condition of that, when you have a perfect contact, so wherever you have a perfect contact, you and the contacting material cannot have the different velocity. So if you want to move, this would also move. If this is fixed also, you cannot also move also. This is the condition called no slip conditions. So no slip condition means wherever you have a perfect contact, your contacting surface and both the contacting surfaces should have the same conditions, maybe same velocity. So if you see this particular figure here, so in this case you have a plate which is marked at the black one here. Now this is the fluid which is coming somewhere far away point. So initially the point, this fluid would be far away here. It will have same velocity. So you can see this, the arrow, the length of the arrow is characterized your magnitude of the velocity. So you see that from here, there is no change here because these are far away from place. So these are not means you can say affected by the contact of the plate. The time you will come closer to the plate, your velocity will keep on the decreasing, and you can see from this velocity profile here. Here you have a slight means full velocity, then it's keep on decreasing and decreasing. At the time you will reach the contact or plate is becoming zero because the plate is stationary. So this condition here on the contact surfaces is called no slip condition here, which is in case of the stationary body, velocity comes to zero. In case of the moving body, so it would have the same velocity of the moving body. Fine. So you can see in this dark figure here, so as you will see on this particular here and this particular shape here, so you see the velocity at the edges everywhere is zero. You can see here from here to here the zero. After that is increasing. So that's called the no slip condition, the visual, actually the demonstration part here. Second, you see here you have a body here. So your fluid is coming from this side, and here the fluid is completely in contact of the body. After that, because the shape looks something of the spherical type of thing. So here you can see that your fluid is getting the separated from the surface. You see that this is the surface, this is the fluid here at this particular point. At this particular point, fluid is very much far away here. So you can see from here, wherever you have a abrupt change in surface, your flow separation would occur, means the flow would not be in contact of the body wherever you have abrupt change in the direction of the flow. So here this is called the separation point where the fluid is leaving the surface. And why is it? Because here the fluid is moving in this side continuously, just like you can actually bend this paper here this way. So let's say you are moving from this side, so here you have in contact. Now you have a tendency that Newton's first law and all this. So whatever the direction you are moving initially, so you will try to move in same direction only. So you have here you will try to move this side, but your surface is this side, so you will not fall down immediately. So it will take some time to you to fall down. So this much gap is called the separation point here only. Fine. Did you understand the separation point?
Yes, sir.
Yes,
Yes,
sir.
sir. Yes, sir.
So, and the next concept here is boundary layer. Boundary means, let's say in this particular figure, you see, if you see this velocity profile here, so in from here to here, there is no change in velocity. So it means you are free to boundary. Now, after that, from here to here, the velocity is continuously decreasing, right? You can see this one, right? The figure top right figure actually. So here you see this in this bottom side here, from this point to this side, the velocity is continuously decreasing, and now it is going to zero. So this particular thickness of the fluid from here to here, in which the velocity is getting affected by your contact surface, is treated as the boundary layer. And this is the boundary layer we always take care as a chemical engineer part, because this is the maximum hurdle for all sort of the problems in engineering applications, because sometimes we do the heat transfer. So in case of heat transfer, you heat the metal pipe from the outside. Inside of that, you are flowing a fluid, and this boundary layer would also form at that particular place. So it means that at the perfect contact of the cylinder, your fluid is not at all moving. So you will not have better heat transfer. So you have to decrease this boundary layer as low as possible, so that your heat can be transferred at a faster rate. Same thing for cooling part also. You want to cool from outside by putting some coolant, and once this boundary layer would form, this create the problem. Fine. So this boundary layer need to be broken out somehow. More is the viscosity of the fluid, more would be the thickness of the boundary layer. Fine. And you see that in this particular range, only there the velocity is getting changed with respect to this y coordinator, y coordinate, and this is called the velocity, the gradient. That the change in velocity divided by the distance y is so delta v upon delta y is being treated as a velocity gradient. So this gradient would only be present only in the boundary layer, because beyond this particular point here, you see at this particular point, there are no change in velocity, so velocity gradient is zero. Fine. Now this is some old examples in the beginning that initially people has constructed the pipeline with the clay, because clay was the easiest the material in the ancient time which you can mold. After that the metal pipe came, then concrete pipe, then these days you have a lot of PVC pipes and all this. So this is some Pergamon pipeline here. So this pipeline clay pipe was constructed 13 to 18 in centimeter in the diameter. And this example you might have seen, you might have not, because this has vanished in from the operations a long time back when I was in seventh or eighth class only. So in blazes, you have they want to take out the water from the bore well. So in that case, you have this flywheel. They want to move it, and the buckets are connected in that way. And then you can rotate the wheel in this side, and then this wheel will move this side, so bucket will come and fill it up. This is the reverse of that. This is being used for coal mining. So what they have on this particular wheel here, this one, they are filling the water in these buckets so that this wheel can move downside. And uh, and this particular, this you have a crane type of thing which will take the ore from the mine, which can lift it up. So one side you are filling the water, other side this will fall down, and this you are just working with the help of fluid so that you can take out your mining ore from the mines to upside. So you can see this particular bucket here. So this goes to the mine side, and from there this is being filled. Once it is filled, then you start pouring the water in the buckets, and this wheel will move in this side, and finally you will lift up the mining material actually. Now this is the scientist here, because so far we have talked about streamline and streamline flow and all this. So Osborne, the renowned by the first scientist who has visually the demonstrated streamline flow patterns of the flowing fluid. So this is his original, I mean the apparatus here. So here you have, he has a glass tube here. Inside of that, he has put a dye molecules in that on the flowing fluid, and then he controlled the flow rates. And he said that below a particular flow rate, dye goes in a streamline pattern only, just like a thin line. And as you will disturb the flow to the higher side, that pattern changes zigzag pattern. That is called something transition flow, and slightly more than that, dye will completely disperse in the fluid. So he visually demonstrated these flow patterns of the flowing fluids. So based on that, he gave the number which we were talking in the last class, the Reynolds number, right? So the Reynolds number is given by him only, which characterize the flow patterns. So below a particular point, less than, let's say, 2100, that number, it is the streamline flow. And 2001 to 2300 is called transition, and beyond that, turbulent. Now these are the another examples where due to of poor designing of that, some of them could not succeed. Just like your Wright brothers, they have made this flight could not succeed for a long time. They have made a lot of things here. So due to failures of the designing of this paddle blade something, then these days you have the modern wind power mills. So wind power in India also we have a lot of wind power plants, but not on a very large scale actually. But we use this one just to extract your crude oil. So crude oil, they have these type of the turbines here, actually wind turbines. So this you have, let's say, Oklahoma wind power plant here. This is the means production capacity is 1.5 megawatt of each wind turbine. Now we want to classify the fluid flows. That how do we classify? So classification can be done on various parameters. One parameter is that let's say based on the property of the fluid, Some you can say the viscous fluid, some is you can say the non-viscous. Non-viscous means ideal fluid here. So ideal fluid, you are just talking that viscosity almost tends to zero. So generally, no liquid have that condition. Only thing you can say that gases will have low viscosity part. Liquid also water have actually nearly one. So in that case, then you have highly viscous. So in that, based on viscosity, you have classified two ways. One is the viscous flows here. Viscous flow there, the flow in which the frictional effects are the significant. Frictional would come only because the viscosity, because viscosity is the parameters which will try to oppose the movement of the fluid particles. Just like in case of solid, you have the rigidity constant at that particular part. So the rigidity constant is the constant which oppose the distortion of the solid block, right? Yes or no?
Yes, sir.
Huh.
Yes, sir.
So in case of fluid also you have the viscosity and which will always try to oppose. So oppose, how would it do? You are applying some force to move it, so fluid will provide the opposite force to cancel your force. So these in terms of that is being treated as the frictional effects actually. So that's one way. One is called inviscid flow here. So inviscid flow is here where you are talking that that frictional effects are the negligible here in that particular part, or the losses in the motion of the fluid by the surface or by the viscosity are almost equal to zero. So that's called, something is called ideal conditions, just like ideal fluids. So ideal fluid, you are just saying viscosity tends to zero. So that is some hypothetical condition. Practically, it doesn't exist actually. So you see this particular figure here. So here you can see this one you can see a pipe here. Outside of that, the fluid is flowing from this side also and top side also. Now you will see in contact of this pipe till this particular point here, your velocity is getting affected by this particular contact. So this particular region here is being treated as viscous zone or the viscous flow, or you can say the boundary layer part here. After that, you see from here to this particular point, there is no change in velocity or flow patterns here. This is being treated as inviscid region here, because viscosity and surface contact cannot control the motion of the flow here. So this is being treated as the inviscid flow part. So viscous flows are, you are treating here close to contact, where your frictional effects are very significant. Beyond that, you are just treating the frictional means effects are the negligible here. So you are treating that in the inviscid flow here. Fine. Then further class, so the previous classification was the viscosity, or based on the frictional means effects. Next classification we are doing based on the flow, whether you are doing flow inside a particular channel or pipe, or flow outside the channel, or the open to atmosphere. So based on that, you have taken two here. One is the external flow here, where you have external flow, you can say, let's say this, you can roll this particular thing, this is the pipe here. So in that case, you have the pipe. So the time you will flow inside the pipe, this is called the internal flow. The time you will flow outside of that, that's called the external flow here. So external flow is just like this river or canal also. This is also being treated as the external flow, or the, you can say, the open channel flow actually here. So a purely external means this only. This channel should be closed and flow should go outside of that. That happens in case of your geyser actually. So geyser, you have this one, you can treat this as one of the heating rod here. Outside of that, your fluid is flowing here. So you can see at this particular point, the fluid is coming inside. After that, this fluid is moving this side and this getting the separated from here. Now this is the part here which will have slight vacuum type of thing because the here will not be much here. So the flow on this, the outside of a particular contact is called external flow only. Fine.
Yes, sir.
Uh, Next classification you can do further on property of the flow, just like compressibility, because anything can be compressed depending on the magnitude of the force. Fine. Yes or no?
Yes, sir.
Yeah.
Yes, sir.
That have some criteria that how can a particular fluid can be treated as a incompressible or compressible. So first criteria we say for compressible means its density should remain constant. It should not change during the operations or during the experiment which we are performing. So that is the first definition here. The density of the flowing fluid remains nearly constant, right? So generally for the liquid case, it happens actually for water, petrol, or any the liquid here, oil also, if temperature is not changing very high magnitude, so its density would not change. Now compressible flows, here you see that where the density changes significantly, and best example is for gases, just like your now gases here, but generally if you are talking about the flow in gases, so best example of that is your all rockets or flowing bodies because they flow in air actually. So air is a combination of the gases, and finally you are talking about the air, and now its density can change depending on at what magnitude your body is flowing. Just like this particular rock, this particular you can say the rocket here for this time being. So this is the flow patterns of the air here. Now here you will have the highest velocity here which is getting hit here, so this will try to compress this particular air. Now to classify compressible fluid in case of the flow here, we have the come up with the one number here, Mach number. So this Mach number classified based on this formula here, the speed of the flow divided by the speed of the sound in a particular medium. Let's say you have medium is for time being water, and water is flowing with some velocity. Now you want to have a penetration of sound in that particular the flowing water only. Calculate the two, and the once the ratio is coming equal to one, that is being treated as the sonic flow. Means sonic flow means you are moving at the velocity of the sound only. That is called the sonic only. Sonic is coming from sound only. Then you have the subsonic means the Mach number is less than 1, Mach number greater than 1, the supersonic, and Mach number very, very greater than 1, the hyper supersonic. So hyper supersonic flow happens in case of rockets, your all the satellites, because there you have velocity extremely high. So most of the time for incompressible fluid, you should be in the region of the subsonic flow where Mach numbers should be less than 1 actually. So if it is Mach number is less than 1, then you can treat the flow as incompressible. Means compressible fluid can also be treated as incompressible if Mach number is less than 1. Fine? Are you getting
Yes,
this
sir.
point? Huh.
Yes, sir.
Sir, please
So
re-explain.
uh, actually most of the time we are talking about the aerodynamics part where your fluid on the outside body is compressible, just like you have gases. Now we have come with this parameter. If this Mach number is less than 1, the property or compressibility of that medium doesn't change much. Therefore, that compressible medium can also be treated as incompressible if Mach number is less than 1. Is that fine?
Yes, sir.
because that
Uh,
incompressible assumptions or calculations make your calculation easier and the simplified. Next classification is based on the flow pattern, the laminar versus the turbulence. So just like a flow
Sir,
pattern here, Balo,
sir, I would like to ask,
yes,
hello,
say.
am I audible?
Yeah, you are audible, but voice is not much clear. But you can say,
Sir, I was asking about that last slide.
hmm, yeah, this one. Hello, hello, hello. Do you have?
Am I audible, sir?
Yeah,
No.
network. Yeah. You can
Sir,
say
in
now.
supersonic flow and hypersonic flow, both are greater than 1.
Both are greater than one, but you say one is just greater than one, other one is too much high. Just like let's say more than one means you have 1.1 is also more than one. Fine.
Yes, sir.
One case you have 100.
That is
So you see
also
the
greater than.
magnitude of 100 is you said the 100 times. So the once you put a greater and greater sign double means you are practically magnitude is more than 50 times or 100 times actually. You can say that. So that is the excessively high condition here, or that happen in case of your the rocket launchers and satellites launchers. They move with a very high velocity just to leave the Earth gravitational force, right? Practically 10 kilometer per second, something, right?
Okay, sir. Thank you, sir.
Just lead to leave the I think the I mean the orbits of the Earth. How much velocity you need? Any idea?
So
11,
it's 11.2
escape velocity
11
kilometers per
11.
second.
Yeah. Kilometer per second, right? 11 point something. So
Sir,
so next,
sir, the speed of fluid depends on the on the shape as well, no, sir. The object we are launching on the moving. So the Mach number is combinedly defined by the shape and all the speed of the object.
so in this case, the speed of the object, yeah, because the you say the air outside the object, just like in case of aerodynamics. So your air is you are treating most of the time stationary part there. Only your object is moving. So object velocity, yeah, it matters, and based on that only it is being calculated.
Sir, I have heard about these numbers in the missile system
Yeah,
somewhere,
missile
sir.
systems, these are very significant. All you can say, all bodies which moves in this means atmosphere, these the numbers are first thing which need to be calculated first. Based on that, they do a lot of part on the designing part, how to control this actually.
Thank you, sir.
Okay, yeah. So next
Excuse me,
class,
sir. Uh,
yeah.
does the compressibility of a fluid have anything to do with the change in volume?
Yeah, because once you have, because without change in volume, the compressibility cannot come.
So, sir, what happens if we?
Because the both are interconnected. Because once the volume would change, only then you can calculate the density. Because the density is mass upon volume only, right? So mass is a conserved quantity. Only thing, if you have a change in volume, only then its density would change.
So then, can't we change the volume of a liquid and convert it
Uh,
into a solid?
so in that case, it will become the solid. If you want to freeze it, by you can freeze water, it will become ice. So it will become the solid at that particular time.
But we are assuming here that water is non-compressible.
Yeah, water is non-compressible under normal conditions at, let's say, between, let's say, 4 degree to, let's say, 35 and something in
Okay.
that particular condition, because in that particular zone its volume doesn't change much, or density, because the
Okay, sir.
density is the function of temperature only. So the kinematics or the mean free path of the water molecule doesn't change that significantly in this particular temperature range. Suppose your temperature is very high, let's say 50, 60 or 100. This assumptions of the incompressibility will not sustain at that particular point.
Okay, sir. Thank you.
Okay, yeah. So next classification of the flow is based on the flow pattern. One is the laminar flow here, one is turbulent. So the laminar flow you might have heard long time in the different way. That's you have heard in terms of the streamline flow, right? So the streamline flow is being treated as the laminar flow. So where you have a flow is flowing layer by layer pattern, and each layer are flowing parallel to each other. They don't intersect the path of subsequent the layers. So that is called the laminar flow. Fine. Next is called transition here. So you see the third figure here. Here you can see there are no fixed this one transitional part in this particular part. The figure number 2 here. So here transition means the previously you can see the layer here clearly. In this, you cannot see the layer, but some part you can see that this particular zone here, somewhere here. So you have somewhere in between of this one, and there are no flow pattern, fixed one. So layer are moving something up and down also. So this is called a transition part. After that, you create the disturbance something, or you increase the velocity, and then you will find the third figure here that is called turbulent here. The no flow pattern, everything has been the mixed up. And how can you identify the flow pattern? Either you can put, let's say, a colored element here, just like the Osborne put in his practical, the Renault. So he has put a dye molecule there, and of same characteristics. Same characteristic means especially same density, so that it should not sink or should not float. So the time you will leave that particle at that particular position, which have same density and should not dissolve within the fluid, then it should go straightly in the same pattern. So these are the practical. We also have in our course the dye practical, how to identify the flow pattern in a flowing fluid. So we will identify all these flow patterns in our practical. So these are the means classification: the laminar flow, turbulent flow, and transition flow. Fine. These are based on only the flow patterns, and based on that we have come up with the number here, the Reynolds number only. Okay. So
Yes,
the
sir.
laminar flow, what would it give? Because you have heard it, this happens only in case of the ideal fluid. So ideal fluid means your practically your viscosity effects are viscosity effects are negligible or high or something. How would you
Yes,
maintain this flow pattern?
Negligible.
Suppose the viscosity is very, very low, what will happen?
Sir,
Hello?
laminar flow, laminar flow.
Streamline flow.
Yeah, viscosity, if it is high, though, if you will create slightly the disturbance in the fluid will not get disturbed. It will move in the same pattern. Fine. Therefore, you have here the word here, the flow of high viscosity fluids such as oil at low velocity is treated as laminar. Next is this one, the natural flow, or one you have the forced flow. Natural flow happens in all conditions, just like in your room, in my place also. Every time you have the flow, wind is blowing there, right? So the natural flow is flowing by its own. You are not creating any disturbance from your side. And how does it happen? So it happens by two ways. By one is change in the density. Let's say you want to go from hotter body to the colder body. So the hotter body would have the low density and colder would have the high density. So high density one will sink and low density would go up. So that comes under the category of the natural flow also, just like so you have this happen here, this you have word here, buoyancy effects. So buoyancy means low density thing would go up, means float, high density thing would sink. Okay. So just like that, when we are coming from a hot atmosphere, just like in this time, the outside climate is very hot. So our body become hot. The time we come home, we turn on the fan immediately. Why is it so? Any answer? Why do we turn on the fan?
So to cool our bodies,
Yeah, but how? It was cooling already also.
to improve
Sir,
the rate of evaporation of water.
Yeah, actually, Sanjana, you want to say something? So in this case, actually, the previously without fan also, your body was getting cool, but only because of the natural flow. You are not doing anything. Your body was hot. Outside of your thing would be slightly colder. So heat from your body will go to the colder side and it will take its own way or pace or time. That's called the natural flow path. Now, what you did with the fan, you have just created the disturbance from outside that is called force flow here, the force convection, and moreover, and then you are getting cool at a faster rate. So force thing means you are providing some external force to make it flow. Fine. Say yes or no, Alp. Otherwise, I feel
Yes, sir.
that what
Yes,
about?
sir.
Sir.
yes, sir.
Yes, sir.
Then you have further
Sir,
classification. Huh.
sir, this is how we create the thermal images. Is this the principle?
Yeah, thermal images based on thermal radiations coming from the body actually, and that happens in case of where the temperature is, let's say 2000 degree, 3000 degree and more. So no thermometer and material can survive at that particular point.
No, sir. Thermal imaging is
Huh.
also used in detecting the peoples around by their heat signature.
Aha, that can also be done, and the lot of the things are coming only because of non-contacting things. Non-contacting things are hygienic also. Just like your these days you have in Corona time, you have a radiation meter, right? So that also giving the temperature, non-contacting one. And same thing, thermal imaging of the body can also be done because as you will be far away, your rays will go to the different side, the transfer of the heat, and next side when we come in contact with the body, then it would be the different one. So you can have that particular thing also. So next classification based on time, because what we happen all the time, we want to say that how things are getting changed with respect to time. So here with respect to time, you have two classification. Either things are changing with respect to time or not changing. So let's say in this particular figure here, this one figure number A here. So if you are focusing in this particular part here, let's say in this particular part here, this part. So here things are totally changing with respect to time. As this object is moving from this side to here, This pattern here is completely changing. Here it is smaller, then bigger, and no fixed pattern also. So this can be treated as actually unsteady state part. Now see for this part here. This part, this is going in this particular part here, and you see this. This is no change. If you see here, so the if let's say of a fluid part, if you are talking about the fluid, so if its properties, property means any property, just like its density, its viscosity, its velocity, are not changing with respect to time. So what the best way? Just calculate the derivative with respect to time only. Any function, just calculate the derivative with respect to time. So if that comes out to be zero, it means that particular flow is steady only. If time derivative is not zero, then it's called unsteady. Fine?
Yes, sir.
So this is the simple definition. Just see the dependent on time. The time we were doing on Tuesday that Bernoulli practical. So I also told you there that we will take the height of the fluid in these particular tubes, and then we will wait for a steady state. We will check it after 5 minutes, then after further 5 minutes, then maybe one more further 5 minutes, and if there is no change in height, it means steady state condition has been reached. So steady and the unsteady, these also mean the matters a lot. Just like a pump, we are buying a pump from the market, and what we need a pump, we want the steady operation from the pump. Means, let's say we have turned on the pump, we want the supply at that particular end. So if we have purchased a pump for 2 meter cube per second flow rate, and if it is not giving that constant flow rate with respect to time, so that will not serve the purpose. That is called unsteady state operation of that particular pump. It's not at all good. So you need that its output should not change with respect to time also. That would call the steady state condition of that particular pump also. So steady state conditions are needed in most of the the operations here, and then you have some of the devices here. Let's say your turbines, your compressors, your boilers, your condenser, heat exchanger operations. First you have time dependent. After the some time they are maintained as a steady state, because after the steady state only you can get a continuous output without any fluctuation. Just like your car. Initially you gave the pickup, then your mileage would come only the time you will run at steady state or a constant velocity only, speed only. Let's say if you will move only at 50 or 40, your mileage would be good as compared to doing fluctuation. One is 60, one is 80, one is 100. You're not at all, there no mileage of that. So steady state operations are always advisable. Fine.
Yes, sir.
Yes, sir.
Then you have further classifications based on the dimensions. Let's say currently you have the good figure also in the PowerPoint. Let's say this is there. Now let's say you are flowing completely in this parallel to this, the axis of this particular the notebook. It means totally in one dimension here. If this velocity is only getting changed only in this side, is one dimension. Suppose there is some fluctuation in this side also, but is going finally to this side, it become now two dimensional because there is the change here in xy plane. Fine. The third one could be that there could be in this way, that this way is going in all x, y, z directions, is changing in all three sides. Then it become now three-dimensional part. So just see here, the first classifications you have here, a flow is said to be 1, 2 or 3-dimensional if the flow velocity varies in 1, 2 or 3 dimensions. Means, let's say you have a velocity, so velocity can have the x component, can have the y component, can have the z component. So if you have a component of y, only component of y, it will become totally one-dimensional in direction y. If you have y and x component, then it will become two-dimensional in xy plane. If you have x, y, z, all three, then it will become three-dimensional here. Now you see here, this is a long tube here, long pipe. Now you see in this particular part here, in the beginning, the fluid is just entering here. Now you see in this particular part here, this one, velocity is totally flat here because the fluid is just entering here. So all fluid particle would have the same velocity here. After that, due to contact or the no slip condition here, that velocity at the edges is decreasing and decreasing, and after some time, you will say after a very long time here, you see from this velocity, the second last velocity profile and the last velocity profile, this one, there is the no change between here. You can overlap these two pictures. So after that, you will say now this is the steady state operation here. Now what you see in this particular point here, what is the difference between here to here? Figure number, let's say, starting to 1, 2, 3, 4. What is the change here? From starting till figure number 4, what are the changes?
वेलोसिटी वैरी कर रही है
Yes, velocity is varying.
डिफरेंट लेयर डिफरेंट
Another
लेयर्स की तो लाइक
part also, that's fine. So if the layer by layer velocity is the changing, so the layer by layer coordinate is r only, right? Because if you will go from the center to this upside, it means you are going to the layer, right? Yes or no?
यस सर
So that is the function of r. What about this side? In horizontal side here, in the z direction also, here you have let's say different velocity. Here you have different velocity. Here you have different. You see the arrow. You see this arrow length here. Here this is the different length. This is the different one. This is different one, and finally this is this one. So at a position r, your magnitude of velocity is also getting changed with respect to z, because at this particular z you have this velocity. At this z you have this one velocity. At this one you have this one, right? So your velocity at a particular streamline or a particular layer is getting changed with respect to z also. Say yes or
यस
no,
सर
right?
यस सर
So in this particular figure, 1, 2, 3, and 4, your velocity is getting changed with respect to r, at the same time with respect to z also. So this time your velocity profile is two-dimensional in r and z. Now you see the second last figure, this one and this one here. These two figures completely overlapped. So in this particular part, the velocity, if you will change from this position to this position, velocity is not changing now with respect to z. You see that this the magnitude here and this one magnitude both are same. Can you see this?
यस सर
So in this case, it means your velocity is not getting changed now with respect to z. It is just changing with respect to r. If you will go from the center to this the walls of the pipe, your velocity is the highest here, then decreasing, and then it becoming as zero at the pipe wall, right? So from this point onwards, your velocity is just getting changed only with respect to r, right?
यस सर
So now this flow is becoming only one-dimensional, is a function of r only. So initially it was two-dimensional, then it is fully developed flow. Now after that it has become totally a one-dimensional flow. So this way we can identify the dimensions of the flow. Fine?
Yes, sir. Sir, we have to
Yes,
take next class.
Yeah, I know. So we will close at this particular point here only, and if you have Any doubt you can ask, and or you can ask in the next class. That tomorrow we have the tutorial class also there. So
Yes.
tutorial would also be taken as a class only. So because that is the combined one. So all of you should present there.
Okay, sir.
Sir. Okay, sir.
Okay.
Okay,
Anything you
sir.
want to ask?
सर वो कार वाला समझा दो एक बार जो लिखा हुआ है मतलब क्या
क्या?
कार डायग्राम में है ना कि 2D फ्लो कैसे है वो
This
समझा
one.
दो
This one, carbon, you see at this, when you are very much far away from this car, you see the velocity here, that is the completely a streamline flow pattern. So this is completely a one-dimensional flow here, this one.
ओके सर ओके सर
As you are coming closer to car body and body, your this flow pattern is getting changed. One is this, the horizontal to hai, this is the direction is one is the horizontal, but at the same time is going vertically up also. So it has become 2D here. So from here to here, it has become 2D flow here. But everywhere you see here the streamline flow. These the streamlines are not crossing the each other's path. You can see here the path.
यस सर
These are parallel. So this is here in this range is the two-dimensional flow, and beyond that it's completely a one-dimensional flow.
सर
Okay.
इट इज लिटिल एक्सेप्ट नियर द टॉप एंड बॉटम सर टॉप पे क्लियर हो गया पर बॉटम पे कैसे 1D है वो लिखूंगा
Bottom is this one, right?
तो टॉप फिर कौन सा
Top is this one here, this one, top layer, this top arrow only.
ओके
Okay. It means much more far away from the body actually.
ठीक है ओके सर
Okay.
यस सर थैंक यू सर
Okay. Bye.